Okay. Welcome, ladies and gentlemen, to our special session on innovative calibration. As you can see, I am not Professor Sommer. Unfortunately, he couldn't make it here today, and I was asked to share this session. We will have 4 talks in total. The first presentation will be by Dr. Ulrich Kaiser from University of Applied Science in Lörrach, and he will talk about from self-diagnosis to in-situ metrological verification. Deutsch is yours.
Okay, thank you for the introduction. The topic is already mentioned. It deals with a method to reduce the number of calibrations or justifications or adjustment you have to make for instruments. Before I get to the topic, I want to tell a little about process sensors. And what is this? This is a chemical park or the chemical company of BASF in Ludwigshafen. And what do you think, how many sensors are there installed? Can you have you an idea, somebody of you? In the total area? Maybe you get a candy when you are right. How many? 10,000, okay. Another number? How many? More, okay. Yeah, more is fine, né? But you won't get a candy for that because it's not precise enough. Okay, it's more than 300,000 sensors. And these 300,000 sensors, most of them has to be calibrated or adjusted. And this is a lot of work and I don't like it. No? And now I come to the topic of digitalization for process sensors. What process sensors are, I will explain it later. No? First of all, I want to mention a study which was published 2 or 3 years ago. And this was made by all important chemical producers and pharmaceutical producers in Germany, together with producers of process sensors. And I come out with one result or one recommendation. They say we need more digitalization in our sensors. And this is written, we need a high degree of condition monitoring or self-diagnosis. That means they said when you have to use new sensors, have to use process sensors, you need sensors with self-diagnosis. What means self-diagnosis? And in order, a normal or a standardized process sensors only has one channel for communication. It only communicates the measurement value. And in order to also transform from the process sensors other information, for example, for self-diagnosis, you need another channel. And this is defined by the NAMO. The NAMO is the organization of all German chemical companies that bring together. They have defined a new way of bringing information from sensors to the control unit. And this is named NOAA, NAMO Open Architecture. And I just will show you how it's going to work. The communication for process sensors is still the very easy communication of 4 to 20 milliamps. This is a technology which was invented a few months after the Second World War was over in the 40s. And this is still the dominant technology of today for the communication because it's very robust, but it's not very innovative. No? And so, and now they use another way, an additional communication path to connect sensors for more information than just the measurement value with the control unit. What I'm going to tell about, this is just to introduce a little, tell about what is process engineering processes, diagnosis, IoT ecosystem, and then I come to metrological properties and how can I improve the metrological properties in order to reduce the number of calibration. And this is the main topic of what I'm going to tell about. Let's start with process. What is a process? For some of you who don't be very familiar with process sensors, a process is a set of interacting operation in a system through which matter, energy, or information is transformed or stored according to a standard. And you have, in easy said, you have in one industry you have a separate process or process where you deal with parts. Maybe in the car industry you put together parts, and in the process industry you put together material, flows of material. And you have it as an example. A typical process is you have some raw material, maybe milk. You put it in some process and you get out cheese or something like that. Or you put in some bacteria and some sugar and you let them work and it comes out insulin. No? This is the way a pharmaceutical company is working. So, and in order to control this process, in order to monitor this process, you need sensors, and these are process sensors. And these sensors are put in the process, inline sensors. And then you understand why it's maybe very complicated, very cumbersome to calibrate these sensors. You have to put them out. You have to stop the process. So when you come to a chemical company and say to the people, I have a sensor for you which you don't have to calibrate, they will do everything for you want. No? So, and this is the story. No? Okay. This is an example for process sensors, for flow, for level, for pressure, for chemical information. No? Okay. A standard sensor is very easily designed in this way. You have an excitation, you have a sensor system, and this works together, and then you get the measurement data out. And in order to diagnose it, you need more. You have a diagnostic system which also has information from all the parts of the sensors, and this creates diagnostic information. And this diagnostic information is recorded in this new NAMO system, is going to a cloud system. Yeah, and this we name IoT, information, industrial IoT technology, no? IoT architecture. No? And this you have to buy, for example, you have here an IoT architecture, and then you have certain applications in this IoT systems which deals with sensor data, or with sensor information data, not sensor measurement data. And for example, you have diagnostic information according to a NAMO standard. This is generated by such a system. But this is not the story today. No? Yeah? What I will first will give a little summarize what I have told so far. It's the second channel for process sensors, besides the channel which is for the measurement value, is a suitable architecture in the basis for the use of extensive diagnostic capability. And this is standard. It's going to become more and more a reality. All companies for process sensors are following this concept. The process industry can then use this function efficiently. They want to have more information of the sensors. But now my question, which I will deal in the next slides, how can metrological properties, in addition, be used to pure diagnostics? You have a system which does diagnostic, which says, okay, your sensor is out of order because of this and this. But I want to have information about the metrological properties, about is this process sensor still working in the proper measurement uncertainty? Yeah? Does it generate the same value, the right value? No? And then comes really the question, all components, and the answer is, or the question is, how can metrological properties be tested in addition to pure diagnostic? And the answer is, all components of a system, of a process sensors, which contribute to metrological quality, everything which affects the metrological quality, the right value coming out, must be checked against internal references. This is the goal. And have, for example, voltages, frequencies, phases, amplification, but also mechanical parameters. And I show you some examples how it can be made. For example, you measure a frequency. You have a frequency in your system, and which has a certain effect on the measurement value. And you can check the frequency just easy by having a second frequency and compare them. And when they're out of order, when they're different, you have a problem. You say, my meteorological quality is not in order anymore. No? Then you have check against internal reference, for example, a phase. You have a phase measurement. You have also a system to measure the phase. Or you have an output. You say, I have an amplifier and check what is getting into the amplifier compared to what is coming out. You may have something to measure a voltage. No? But the important information is you cannot check everything in a process sensor. You only have a fraction of all meteorological quality determining parameters. You can grab a part of them, not 100% of them. No? Okay, and for example, I prepare here system. You can also get even verification report of what you have measured. No? Okay. Yeah? So again, a stop over what I have presented so far. By comparing with internal references, meteorological properties can also be checked as part of self-diagnosis. You have a self-diagnosis, and by using this additional parameter, you can measure also meteorological properties. But not all components of the process sensors are accessible for this check. Not all. This is important. We will come later to it. And such a review can be documented via an IoT ecosystem. I showed you an example for that. No? And realization of such sensors, of such types, are already available on the market. There are some companies who show that, or they say, I can check on the meteorological properties and I get a document which says everything is okay. But it does not mean that you have to not calibrate it and adjust it. I will come in the next part to that. Yeah? Okay. Calibration. I think there's, maybe you expert know it better, a little problem or a little difference with the term calibration and the term adjustment. I think calibration in English also means adjustment, no? Or you need both. Okay, what I mean with calibration is you check whether the value is still right, and when you do adjustment, you turn on the instrument bis the value is right, until the value is right. Okay, calibration. This is, for example, the calibration of a flow sensors, and this is a machine you need for that. And this machine is so much expensive, it costs 10,000 times the price of a sensor. And my company I used to work for before I come to university has about 10 of these devices worldwide. They cost several millions. No? And so it's really understandable why you don't want to do so often calibration. You don't want to have so much of these instruments, so expensive. No? Besides the effect that calibration is very cumbersome. No? Okay. And now from metrological testing to calibration. During calibration, very easy said, I hope you are right with that from BAM, the entire measuring system is checked against a reference. That is calibration. You measure zero, is it zero? You measure as a high point, you measure at this minutes, okay, you said everything is fine. No? During meteorological testing, many relevant functions, but not all are checked against references. In one cases, to the final measurement value, in other cases, only some internal values. And this is a way, when you have a process sensor, and don't do anything, you have a certain probability of error, which increases with time. You said, I do a calibration, and then I do nothing. And the probability that something went wrong with that your measurement value went out of specification gets higher and higher and higher and higher. This is the idea behind. And in order to keep it within operation, you do calibration or adjustments. You do a calibration, and then it starts again. And you do a calibration, and then it starts again, and so on. And I don't know, typically these time frames, these time distance are half a year, 3 months, 1 year. Yeah? No? Okay. Now, let's look at the same but with the internal testing of internal metrological testing. You also have this curve when you do nothing, but then you do regular metrological internal testing. This looks pretty much the same, but it's getting worse because you don't affect all parameters. Maybe you have only 90% or 80%. There's still a probability going up that it's getting worse and worse and worse. In order to keep this to ground, you just have to do this. You do a real calibration, but very new calibration interval, which is much longer. And just by this internal testing, even when it don't affect all components which are relevant for the meteorological quality, you may have a drastic increase in calibration interval. And this is the story. Maybe here you have every 3 months, then you have maybe every 2 years in order to get to that. And this is maybe my main message for today. Yeah? Okay, the best, of course, would be when you have an internal reference, which is a reference for the measurement value. We are looking at that will come to us. Yeah? Okay, but there is one example for that. This is a temperature sensor which is an internal fixed point cell. And this measures internally all information. This measures the temperature. It has a temperature point, and this temperature point can be used internally to do an internal adjustment. This is available, very successful, but what I would like to have, internal references for pressure, internal reference for fill level, internal reference for flow rate, for pH, for everything. But there is something which goes in this direction. This morning at the conference, I heard a presentation from the NIST, from the United States. And they have a project which means NIST on a ship. And it's not in the prototype phase or research phase, but they are going to have internal references for temperature, for dimensions, for fluid measurements, for mass, quantum optics, and so far. No? And maybe in some years, I don't know how long it will take, maybe 5 years, 10 years, we might have internal references for our final measurement value. And this internal complete calibration is not necessary, an explicit calibration. And then organizations like BAM and PTB may look for another work. No? Okay? But it takes long. Don't be worried. Okay. So I have 2 examples. For example, this is a high frequency reference system which works as a photonic chip. And this is a quantum generated length reference. But here you are able in the future, which is done by NIST, I don't know who else working on that you may buy small chips which gives you internal reference for your process sensors. I think I'm almost done. Yeah, we have a lot of time. Okay, another. No, this I skipped. Sorry, no, this is not so important. Okay, no. So, then we come to the summary, and then you have a little more time to do something else. The second channel for process sensors and an IoT ecosystem, the cloud system, and so on, is a prerequisite for using extensive diagnosis capabilities. And this is already installed in some instruments. This is already made by the manufacturers of process sensors. The self-diagnosis infrastructure can be extended to reference to internal references to check meteorological properties, or the parameters which has an effect on the meteorological properties. This can reduce the need for explicit calibrations or adjustments. Yeah. This I have skipped. Machine learning, this is a research running at the time being. Machine learning methods can make it possible to identify the critical parameters for a calibration condition. Consider, I explained it, we have some time, you have process sensors which maybe has 20 components internally, and you measure all these components: a voltage, a phase, a frequency, an amplification. And you want to know what of these parameters are really relevant for the metrological properties, and this can be done by machine learning methods. No? This is the goal here. No? Okay. Have it? Okay. Self-calibration for process sensors would be ideal, and this NIST on a chip project, which is running some here, and it's going to run, takes its approach. I have only one slide over. Never believe, always test, and thank you for the application. For the attention. No? Okay, so.
Yeah, thank you very much.
Too fast. No? Okay.
We are fine. We can maybe have some questions. I think it's very good to see that avoiding calibration is also an innovation in calibration.
It would be the innovation of the century. No?
Yes. Okay. Are there any questions from you on this talk?
Everything is understood. Very good.
Maybe what would be interesting is, I mean, how established is this whole thing? I mean, how many of these sensors and of the NOAA open architecture is already in place? I mean, I guess we're talking about the brownfield here, right? I mean, it's about updating the machines or is it all about new?
I think the NOAA stuff, this will be in the future, starting with new instruments.
Okay.
But the metrological properties, this is, for example, by my former company, they have covered almost, I think, the entire product program for that. That every sensor has this functionality in it.
Yeah, okay. Yeah. Okay, thank you very much. We will go on in 8 minutes, as far as I see.